So we're going to focus in the situation where we have a nice system of equations. So we're going to drop the non-homogeneous part. And then we're going to say all our coefficients involved are numbers. So there's no functions of t floating around. So in particular, we can write it as x prime equals a times x, where a is a matrix of numbers. Like, okay, great. And our goal is to solve. In other words, what's the solution? What does a general solution look like? Or maybe what does a particular solution look like if we have some initial conditions? And if we go back to our old setting, and when I talk about old setting, back when we first started this class, and we saw differential equations like x prime equals constant x. In fact, it was probably our first differential equation we solved. We said, look, we know how to deal with those kinds of differential equations. We've been doing that. And in general, anytime we see like constant coefficients, we said, oh, exponential functions. So it's e to some constant times t, and we just said, okay, we just got to figure out the right constant. That's what we were doing before. I said, well, look, what's old is still a good idea. We're going to use that idea again. So we're going to say, okay, let's think about what our solution should look like. And we say, well, it should look like some kind of exponential function, but it has to have a vector involved, because these are our vectors, x prime, those are vectors. So the way we turn it into a vector is we take our exponential function and times it by some vector v, where v is a vector of just numbers. We say, okay, that's what we think our solution should look like. And now we start to say, if that's the case, what has to be true? So that's where we start. We say, okay, let's suppose we have our differential equation x prime equals ax, and that our solution has this nice form. X looks like this function e to the lambda t times v. Well, this is a pretty easy thing to take a derivative of, because v doesn't change. The only thing that changes is the e to the lambda t. What's the derivative of e to the lambda t? Yeah, lambda e to the lambda t. So that we have our x prime is something pretty easy for us to compute. On the other hand, we know how to write a times x. That's no surprise. So we know what a times x looks like. So we have that lambda e to the lambda t times v has to look like a e to the lambda t times v. And then we make one more simplification. We say, hey, both sides involve e to the lambda t. Can we divide by e to the lambda t? And why? So can we divide both sides of this equation by e to the lambda t? And why are we allowed to do so?
It will never equal 0.
The beautiful thing about the exponential function. E to something is never 0. And you can divide as long as what you're dividing by is never 0. So we can divide to cancel. And we come up with this really beautiful fact that if we have the solution that we think it should look like, so in other words, if our solution has the form e to the lambda t times v, then it must be the case, has to be, that when we take this vector v, multiply it by a, we get back v, but with this extra number in front. So lambda here is a scalar multiple. So it says that, oh, if you think about a as taking a vector and giving you a new vector, then what's really happening is that you're really just multiplying that vector by a constant. So this is the important formula. Now, no surprise, this has been studied before. And so the good news is we have theory that we can use. So this is what we call eigenvalues and eigenvectors. Now, you look at the word eigen, and you're like, I don't know that word. What is it? Well, it's German. And I don't speak German, but people who do speak German have told me that this really means same. Now you might be like, huh? What? What does sameness have to do? Okay, so here's sort of how I like to think about it. A little picture here. So we're starting in our space. So there's our space, say in 2 dimensions, x1, x2. And we can think of a point as also being a vector. So what A does is it takes old vectors to new vectors. So when we apply this vector v and put it into A, we get a new vector, and that's A times v. Well, what happens is if A times v equals lambda v, what you've really done is you've scaled. So in other words, both the output and input are pointing in the same direction. So that's sort of what's being preserved. It's the sameness of the direction. But the real moral of the story, and this is why we care, is it's super easy to apply A to eigenvectors. Because once you know something's an eigenvector, you say, oh, applying A is the same as just multiplying by a number. Like, wow, easy, I like that. Because I like to think about how I just multiply by a number. So that's why we like eigenvectors. All right. So, some definitions. If we have a matrix A, and we have something that's a non-zero vector V, and AV equals lambda V, then lambda is called the eigenvalue, V is called the eigenvector. You might notice that there's this very bold word, non-zero. Well, why do we care about that? Suppose V were 0. What's A times 0? 0. What's lambda times 0? 0. That's not interesting. 0 always equals 0. So that's why we insist things are non-zero. Non-zero. All right. So that's what they are. In other words, it's exactly this relationship here, just adding the condition that things are not 0. So how do we find it? Well, to find an eigenvalue, or really to really start getting to the whole thing, we say, okay, let's start with the fact we know lambda v is AV. So I can put everything to one side. So I subtract. So I'll be left with 0 is the difference, lambda v subtract AV. Now suppose you hadn't seen what's below here, and you said, oh, lambda v minus AV. What would you want to do? You'd want to factor, right? Because both things have v. And if you factor, you say, oh, it's v times lambda minus a. But what's lambda minus a? It's nonsense. It has no meaning. I'm like, oh, dang it. But now what we do is we add this little extra piece here, this I. So the reason we add the I, well, first off, we're not cheating. I times v, what's the result? V, because that's what the I, remember that acts like 1. And so you should think of it as it's doing what 1 should do. And now if we factor out, we'll have, oh, it's lambda I minus a. And that's okay. So we really come to the conclusion, oh, we need to have lambda I minus a times v equals 0. Now, when is this possible? And it turns out it can only happen if the following is true. We must be in the case where this determinant, lambda I minus a, has to equal 0. Now, why is that? Well, one way to see why this is true is we talked about inverses before. When does a matrix have an inverse? Do you remember? We didn't prove it, but we said it. Okay, columns are linearly independent. That's true. There's another thing we said about determinants. And I gave it away. There's something we said about inverses.
Non-zero determinant.
Non-zero determinant. If our matrix has a non-zero determinant, it automatically has an inverse. if this matrix, lambda I minus a, had a non-zero determinant, then I can find the inverse of this matrix. If I can find the inverse of this matrix, I can move this to the other side and come to the not so surprising conclusion that V would have to equal lambda I minus a inverse times 0. But if I multiply something times 0, what comes out? 0. Which would say V is 0. But what do we know about V? V is non-zero. So that says, look, this can't have an inverse. And so it has to be the case that the determinant is 0. All right. So now we have a plan to find eigenvalues. So what we do is start with a matrix. It has to be a square matrix, because that's the only kind of matrix we're going to deal with. And we look at the determinant, lambda I minus a. So write the matrix lambda I minus a, take the determinant of that matrix. That's a polynomial in lambda. We set that polynomial equal to 0. And we find the roots. Now this polynomial has a name. It's called the characteristic polynomial. I'll tell you that there's a slight disagreement about what the characteristic polynomial looks like. Some people say it's lambda I minus a. Some people say it's a minus lambda I. We say it doesn't matter. You still get the same answers. So I'll follow the convention lambda I minus a. All right. So that's not so bad. It's not so bad. So let's do an example. And we'll come back to this little pro tip in a second. Find the eigenvalues of this 2 by 2 matrix. So we're thinking of this as our matrix A. So the idea is we're going to take the determinant of lambda I minus a. So lambda I, well, since it's a 2 by 2, we'll have the form lambda, lambda, 0, 0, and then minus a for minus 3, 6, minus 7. Oftentimes you skip this step, but I want to do it at least once just so we can see what's happening. All right. So what does this matrix look like? What's the entry in the first row, first column? Yeah, lambda minus 4. Okay, first row, second column. 0 minus minus 3, 3. Second row, first column, 0 minus 6, so negative 6. And last entry, lambda plus 7. All right. Well, that's not too bad. 2 by 2 matrix, we can take determinants pretty quickly, right? Go down the diagonal, multiply. Lambda minus 4 times lambda plus 7. Subtract, go up the other diagonal. Negative 6 times 3, well, that's negative 18, but I'll go ahead and write it like that for the time being. All right, so notice we did get down to our polynomial. What should be our next thing to do? Simplify, okay. Simplify how? FOIL, expand, work it out. So, lambda squared, lambda times lambda. Then we have a 7 lambda minus 4 lambda makes 3 lambda. Then there's a minus 28. Over here is a plus 18. Put those together, minus 10. So there's our nice polynomial, the characteristic polynomial all worked out. Now we're after the eigenvalues. What do we need to do to this polynomial? Set it equal to 0. That's what we said up here. We're going to take this determinant, set it equal to 0. So now we just need to solve this. Well, does this do anything nice? Some people say yes, it does. Maybe that means that we can factor it. How does it factor? Lambda plus 5, lambda minus 2. You can always check. Lambda squared, that's good. Minus 2 lambda plus 5 lambda, that is 3 lambda. And 5 times minus 2 is minus 10. So the roots are negative 5 and 2. So that says our eigenvalues are going to be those roots. So negative 5, positive 2. All right, good. Not so bad. Now, I skipped the pro tip, and this is a way to check your answers. In some sense, it's a way to quickly find your answers if you reason through it. And it says, suppose I want to check to see if I did this right. Now, one thing is, of course, redo all the work, but there's a danger in that, first off, it can take a while. And the other thing is, you're likely to make the same mistake if you've been making a mistake. But here's how you can check it. If you add the eigenvalues together, that's equal to just adding on the diagonal. So that means if you go down this diagonal, well, 4 plus negative 7? Negative 3. Negative 5 plus 2? Negative 3. That's a good sign. They match. They should match. And if they don't match, a mistake was made. Now, the other thing is if you multiply the eigenvalues, that's the determinant. All right, the determinant of this matrix. Negative 10. So 4 times negative 7 is negative 28. Subtract negative 18 is negative 10. Multiply negative 5 and 2? Negative 10. Okay. So there's ways to check your answers. And as the great mathematician has said, you should check yourself before you wreck yourself. So, now we're going to look at something just as a throwback, just to say, what we're doing here should not look that foreign. It's actually things that we've seen before, just in a slightly different context. So we're going to go back to the method of elimination, which is where we use that variant of Cramer's rule on this particular system. Now, if you look at this system, you might say, hey, that looks kind of similar to what we're talking about, because it's kind of similar to what we're talking about. It's the derivative, x1, x2 prime, and if you gather the coefficients, 4 minus 3, 6 minus 7, times x1, x2. So this is, we can translate these two equations into this format here. And you'll see it's the same matrix. Now, if we were doing this by process of elimination, how would our problem go? Well, what we would do is we would take everything and move it over to one side. So our equations would become x1 prime minus 4x1 plus 3x2 equals 0. And it would become minus 6x1 plus x2 prime plus 7x2 equals 0. So we moved everything to one side. And then we break out our notation with the letter D. x1 prime minus 4x1 becomes what? Yeah, D minus 4x1. Then you have the 3x2, the minus 6x1 on the next row. This x2 prime plus 7x2, what is that? D plus 7. All right. And now, if we solve for, let's say we solve for x1. The way we do it is we take that 2 by 2 determinant where we use the d's times x1. And we come over here, replace the first column by zeros. And again, there's a 2 by 2 determinant. Now, this determinant on the right-hand side, because there's a column of zeros, what does this become? 0. Yeah, it's hard to recover from a column of zeros. But now our great, this looks kind of similar to something. Have we seen anything like this elsewhere? It's not the same, but similar. This looks suspiciously like that, doesn't it? What's the difference? Yeah, one has lambda, one has d. But other than that, they're the same. That's not a coincidence. And so if you were to actually work this out a little bit further, you say, oh, this is d squared plus 3d minus 10. It's the same thing. It's just replace lambda by d's times x1. equals 0. And if you turn this into an equation involving r, because you were trying to say, okay, I want to know what my solutions look like, you'd end up with r squared plus 3r minus 10 equals 0. So in other words, what we were calling the characteristic polynomial before, the auxiliary polynomial, when we had just single function, it's the same thing we have here. So these ideas are matching, and they should match. And I just think that's a nice sort of say, this isn't so bad. It's not that different. All right. Well, that's eigenvalues. What else do we need? Eigenvectors. They come together. So you always have to find the eigenvalue before you can find the eigenvector. So suppose you know the eigenvalue and you have your matrix. Then what do? Well, what we really have is, remember, this tells us that A minus lambda I times V equals 0. And so we're trying to solve for V. So the way we solve for V when we have a system of linear equations is, I wrote A minus lambda I. It's lambda I minus A. Now I feel silly because I switched conventions. Okay, but the way we do this is we set it up. So lambda I minus A, that comes from my matrix here. And this bar says, okay, I'm trying to solve for when does it equal 0? The all zeros. So this is a way of solving for all zeros. We saw something like this when we solved for inverses. Same ideas. And now we say, all right, start with that. And what we're going to do is we're going to row reduce. And we're going to do it as much as possible. Now, what do we mean by row reduce? It says we're allowed to do 3 things. We're allowed to switch rows. We're allowed to scale a row by a non-zero number. And the most important is the one that we actually write first. Add a multiple of one row to another. And we do that as much as possible. Now you might say, well, what does as much as possible mean? Well, we really want to get to the point where we say, in every row, it's either all zeros, or the first time I see something that's a not zero number, that's a 1. And if I do ever encounter something like that, where there's a first 1, all the other entries in that column are 0. Now, this has a particular name. And if you've had linear algebra before, you might have encountered it. It's a roof. Actually, that's not what it is. That's the abbreviation. Does anybody know what this stands for? Row reduced echelon form. Yeah. So all you people are like, ooh, cool. Now I can take linear algebra to learn more about this row reduced echelon form. Yeah. It's this. It just means simplify as much as you can. That's all it is. Now, there's a couple things that have to happen. One, you have to have a row of zeros. You can't get to an identity. If you get to the identity, mistakes were made. When I say get to identity, this part right here, lambda I minus A, cannot get all the way to the identity matrix. It's impossible. The other thing is, when you have the remaining rows, force relationships about the entries of V. And so you can take those rows and figure out what must my vector V look like. And so that's how you find your eigenvector. So that's the third thing. The fourth thing is really not a step. It's just an observation that says, if you don't like the fractions that show up, because oftentimes fractions do show up, you can always scale to get rid of fractions. So, because if I have an eigenvector, if I multiply it by a number, it's still an eigenvector. Anything that points in the same direction still works. That's why eigenvectors are nice. It's like everything in that same direction is really easy to understand. So just scale so that things come out in a nice way. All right. Well, let's do an example. Find the eigenvectors of 4, -3, 6, -7 using the eigenvalues previously found. Well, because it's the same matrix we just did here. Okay, so what are the eigenvalues? Did you write them down? What? -5 and 2. All right, so we can do those in any order. Which one do you want to do first? Two? -5? -5. All right. -5. So here we go. Let's start with lambda equals -5. So what do I want? Well, I'm going to construct this augmented matrix. This is lambda I minus a, and then the 0. That's the first step. But of course, lambda here is -5. So this is -5 minus a. Oh, -5 times identity. That looks terrible. Let's try it again. -5i minus a, and then all zeros. Okay, so -5 is going to be subtracting on the diagonal. So -5 minus 4 would be -9. Then we subtract -3, so it makes it a +3. We subtract the 6. And then we have -5 subtract -7, which would be 2. All right, so here's our lambda I minus a for lambda equals -5. So we want to do some row reduction. What can we do? Now the good news is for 2 by 2s it goes pretty quick. So in particular, what do we want this first column to look like? 1, 0. Well, how can I make it look like 1, 0?
Pull 3 out of the top and 2 on the bottom.
Sorry, what?
Pull 3 out of the top and then 2 from the bottom and go from there.
Well, we can do things like that. But if I want to do a 1 here, I want to pull more than just a 3. So somebody said, "Oh, pull 3 from here, pull 2 from there." Yeah, you can absolutely do that. But let's really pull. Keep pulling. How can I get that -9 down to 1? Yeah, to divide by -9. All right. Or I can think about multiplying by -1/9, if you will. So if I just do that, so we'd have 1, -1/3, 0. Haven't done anything to the bottom yet. That's good. Now what? I want to make that a 0. What can I do?
Add 6.
So I can combine rows. Now I can't just multiply a row by 0. That's not allowed because you have to multiply a row by a non-zero number. But I can combine rows. So if I multiply the first row by 6 and add, and if we do that, we'll get 1 minus a third, 0. Because we haven't done anything to the first row. What do we get for the bottom row? 0.
8.
So 6 times -1/3 is -2 plus 2, 0, and 0. You always have zeros over here. And now we're like, haha, that's as far as we can go. We can't go any further. Good. Now you look at this and say, how does that tell us our eigenvector? Now here's the key. This row right here has information. Now you might say, well, what about this row? Well, we'll come back to what that row is. And what we have is we said, look, we have our vector AB. And then we set up this equation. And what you really should think of is that this column is the coefficients of A. This column is the coefficients of B. So that when you read off the first row, it really should be read as A minus 1/3 B equals 0. So A minus 1/3 B equals 0. What does this second row tell you? 0A plus 0B equals 0. In other words, 0 equals 0. But we already knew that 0 equals 0. In fact, it's something we've known for a long time. It doesn't really help us understand anything. So now I say, okay, if a minus a third b equals 0, we can say that means a looks like 1/3 times b. So our matrix, our eigenvector has to look like 1/3 times b, because a is a third times b, and b. Now, we could have also said, oh, this means b equals 3a, so I could have said a, 3a. It doesn't really matter. The point is, we can use that linear relationship to say, our vector has to look like this. Now, you might say, but what about b? Well, what about b? The answer is, we can choose any value for b that we want. So this vector, 1/3, 1, is an eigenvector or any multiple thereof. Now, if you don't like fractions, we can multiply that and get rid of the fraction. So what's another way to think about an eigenvector that has the same direction? Yeah, we can go 1, 3. It has the same direction. Therefore, it's still a valid eigenvector. So we scaled by 3. You can think about we choose b equals 3, but we can choose any multiple we want other than 0. Okay, so the process, set up our relationships and find some non-trivial combination of the entries that are forced, and that reduces it down. We'll do more, don't worry, because what else do we have to do? Yeah, we have to do lambda equals 2. All right, good. So, here we go. We're going to take 2i minus a. So we'll go a little bit quicker this time. So we're going to take 2 times the identity matrix, subtract this matrix here. If we do that, we'll have minus 2, 3, minus 6, and 9. 0, 0. Yes? Okay. Start pulling out some things we can do with row reduction. What are some things we can do? Okay, we can multiply the first row by negative 1/2. Can we do something with the second row at the same time? Well, we can multiply the first row by what and add to the second row? Negative 3. So if we do that, those two operations simultaneously, the first row will become 1 minus 3/2 and then 0. The second row, minus 2 times minus 3 is plus 6, minus 6, 0. 3 times minus 3 is minus 9 plus 9, 0, and 0. All right, so we say, aha, the second row doesn't tell us anything, but the first row says there has to be relationships involved. And our relationships have the following form, namely, a minus 3/2 b equals 0, where again, we're still thinking of our vector as the form ab. So what does that say about our vector? Well, it says a has to be 3/2 the value of b. So, in particular, we have any vector that looks like 3/2 b, b is an eigenvector. Pull out the b, you get 3/2 1. All right, so there's a perfectly valid eigenvector. What's a better choice, perhaps? 3, 2. We can scale. All right. Now, can we check our answers? And how? Let's check one of them. How can we check an answer? Which one of these two do you want to check? 1, 3? Okay, so how do you check without repeating the work? Someone said plug it back in. Plug it back in where? So if something's an eigenvector, the way you check it is multiply A times V and say, what do I get? So 4, negative 3, 6, negative 7, that's our A. Here's our V, 1, 3. So we'll have 4 subtract 9. 4 subtract 9, also known as negative 5. Then we're going to get 6 subtract 21. Negative 15. Now the question is, how do those two relate? They're scalar multiples. What scalar multiple? Negative 5. So in particular, that says, aha, here's my lambda, my eigenvalue, and there's my v again. So I get AV equals lambda v. So you can check your answer about whether or not you actually have an eigenvector. You just say, okay, multiply A times V. Do I get a multiple of what I started with? If you did, life is good. If you didn't, uh-oh, check your work. All right, so we can talk about eigenvalues. We can talk about eigenvectors. And so now we have our plan. It's a great plan. Beautiful plan. It says, okay, suppose we're in our setting, x prime equals ax. Then there's a couple of steps. Let's assume we have A is an n by n matrix. Step 1, find the n eigenvalues. There are n of them, guaranteed. And the reason we have to have n is if you look at the characteristic polynomial that comes from the determinant, it's going to be a degree n polynomial. And that has to have n roots. That's very fundamental. It's actually called the fundamental theorem of algebra. That says we know there have to be n eigenvalues. Okay, great. We know our eigenvalues. Step 2, find, if you can, the eigenvectors. Now, why do we have a star here? Not all matrices do have a full set of eigenvectors. And in that scenario, we have to do a little bit of what we would call bumping. We'll talk about that in a future class. That's not for today. And also when we talk about finding, we want to make sure we get things which are nice. And nice for us means linearly independent. How do you check if something's linearly independent? And that's down here. Throw it into a Wronskian. So if you have a set of what you think are good eigenvectors, put those eigenvectors so each vector is a column, take the determinant. If that determinant is not 0, you're good to go. They're linearly independent. All right, so we found our eigenvalues, we found our eigenvectors. And now we say, well, great. These are a bunch of solutions. Namely, for each eigenvalue and eigenvector pair, we create a function. E to the eigenvalue times t, and then that's times by the eigenvector that goes with it. And they're guaranteed to be linearly independent. Guaranteed. And so that's a bunch of solutions. So the general solution just says combine them together. We use superposition. So some constant times that first function, some constant times that second, all the way up to some constant times the n. All right, good. Now, I'm going to make a quick little note here that'll save us a little bit of time. So there's a little bit of a nice fact. It's a small fact called a factoid. So eigenvectors from different eigenvalues are always, can you guess what the next two words are? Yeah, are always linearly independent. So if you have distinct eigenvalues, then you're always guaranteed that you have distinct linearly independent solutions. You don't even have to do any other checks. It's just automatic. Okay, so now let's throw this at a problem. Solve x prime equals 4 minus 3, 6 minus 7 times x. X of 0 equals 10, 2. All right. Well, some good news is this isn't just any random matrix. We spent a lot of time on this matrix today. What's the eigenvalues for this matrix? All right, -5, +2. And not only do we know the eigenvalues, we know eigenvectors, because that's what we just did a few minutes ago. So for -5, we can use the vector 1, 3. And for 2, we can use the vector 3, 2. We could really use any multiple of those vectors, because after all, in the end, we are going to have these arbitrary multiples coming into play later on. So any multiple works, which is why we just choose the multiples where they look nice. Which says that a general solution to this looks like some constant, e to the -5t, 1, 3, plus some other constant, e to the 2t, 3, 2. All right. Great. Woohoo! Is there anything else for us to say about this problem? Yeah, there's some initial conditions in play. We got to satisfy that. Well, all right, let's do that. So we know x of 0 is 10, 2. So the nice thing is plugging in 0 into the exponential functions is pretty quick. E to the 0 is always 1. So it's some multiple of the vector 1, 3 plus some other multiple of the vector 3, 2. Which, if you look at it, you could really say this is a system of equations. C1 plus 3C2 equals 10, and 3C1 plus 2C2 equals 2. That's if you think about reading the first row, reading the second row. Yes?
Is the x equation, the last one in black, is that like a y or the x complementary solution? And then since we didn't have a particular, just leave it as that for the general?
Well, so this is, yeah, we would call this the homogeneous part. But in this case, the homogeneous part is the everything part. Because there's no f of t. So yeah, we don't need to worry about any particular solution. All right, 2 equations, 2 unknowns, lots of ways to solve it. And so we're going to do it using, again, just practice here, because we need to practice this. 1, 3, 3, 2, 10, 2. All right, our goal is to get down to the identity here. If we get down to the identity here, these numbers are going to be our choice for C1 and C2. All right, so in the interest of time, I'm just going to say multiply the first row by -3, add down. Because I already like the 1. And so let's see, that would be -3 plus 3 is 0. -9 plus 2, I'm not liking this as much. But, you know, it is what it is. -30 plus 2, -28. What should we do on the second row? We can scale that second row by -1/7. That'll give us 1, 3, 10, and 0, 1, 4. Nice. And then we can multiply the second row by -3 and add up. And we'll end up with, well, the second row hasn't changed, 0, 1, 4. First row will be 1, 0, and -2. So that tells us here, -2 is what? C1, and 4 is C2. So our final answer, x of t, is -2 e to the -5t, 1, 3, then plus 4 e to the 2t, 3, 2. All right, and there we go, our beautiful answer. Okay, well that's well and good, but suppose we try this one. Find the general form for solutions of this. X prime equals some matrix times x. Wow. Oh, my gosh. Wow. Okay. And there's a hint. It says the hint The characteristic polynomial is lambda minus 2, lambda minus 1 squared. Well, what does this give us? This is telling us, hey, we're going to tell you the eigenvalues free of charge. What are they? 2, 1, and 1. All right. Well, so let's shoot to find some eigenvectors here. Now, let's do the 1. So, we're going to look at, for lambda equals 1. So again, we're going to take 1 times the identity, subtract a, and then add zeros onto the end. All right, so 1 subtract minus 5, 6. Then it's going to be minus 3 plus 3. We're going to subtract minus 6, so that's plus 6. 1 subtract 4, minus 3. And then we're going to subtract minus 3. We're going to subtract 8. We're going to subtract minus 4. And 1 subtract 5 is minus 4. And 0, 0, 0. Okay, so we set up our system. All right, what are some things we can do? Okay, we can subtract the first row from the second. Is there anything else we can do? Okay, multiply the top row by a 6. Is there anything else we can do? I mean, we don't have to do everything at once, so if you're like, oh, I want to see an update sheet before you tell me anything else we can do again. So suppose we just do that. So clearly these two rows are the same, so they're going to cancel out. That's no surprise. That's why we get all zeros. And multiplying by 6, that's not so hard to do. What about this last row? What can we do? Multiply top row by 8 and add down. And what do we end up with? On the bottom. We get 0, 0, 0, 0. These will always be zeros on the end. We just put it there just to remind us that there's something going on. All right, can we do anything else? No. Now this is actually really cool here. So what we're really doing when we do this reduction here, reduction, is we're getting information about how the eigenvector has to look. So if we are thinking that our eigenvector has the form A, B, C, then these are coefficients. And this is a coefficient for A, coefficient for B, coefficient for C. We're saying that there's relationships between A, B, and C. So they're not arbitrary. Now the last two rows tell us not very much. 0 equals 0 and 0 equals 0. But that first row, that first row. Any row where there's non-zero entries after we've row reduced as much as possible, we get information. What does that first row tell us? A minus a half B plus 1/2 C equals 0. Which says that our eigenvector, well, if we solve for A now, it's 1/2 B minus 1/2 C. Anything that has the form 1/2 B minus 1/2 C, B, C, is going to be an eigenvector for any choice of B and C. Now, how many choices do we get to make? One choice for, why do you say one choice?
I feel like because you have two variables.
Okay, so we have two variables.
So you get to make two choices?
Yeah, we get to make two choices. Good. Two variables, two choices. We get to make a B choice, and we get to make a C choice. So what you can really do is you can say, I'm going to pull this apart. I'm going to pull you apart. And so if you pull this apart, you get B. Well, what's B in this matrix? Sorry, this vector. In the first entry, it's a half. In the second entry, it's, in the last entry, it's 0. And then you get a choice for C. In the first entry, -0.5. In the second entry, last entry, 1. These two are both eigenvectors associated with 1. So we got 2 eigenvectors in this case. Now, probably wouldn't choose those vectors. What were the ones we would probably choose? Yeah, you multiply it by 2. So we would say, hey, 2, whoops. So we'd have 1, 2, 0. And we'd have 1, 0, minus 2 are both eigenvectors associated with 1. Which would say that part of our solutions should look like this. So some constant e to the t times the eigenvector associated with 1, some constant e to the t are other eigenvector associated with 1. And then, well, you can finish up the eigenvector for 2. Homework, I guess. All right, we will start up again next time. Have a good day.